Okay. Um, Hello, everybody, or nobody, as it were. Um, Welcome to our online version of Math MTHE 439. I'm Andrew. I'm your instructor. You can reach me best by email. Can everybody hear me okay? Is it everything configured all right? Somebody just want to say yes?
Yes.
Thank you. There's an on-cue page, which I see some of you have accessed, and I've been pretty careful about trying to put everything that I wanted to on the on-cue page. So I'm not going to say an awful lot today because I don't want to run the risk of contradicting something I've already put on the on-cue page. But there's a few things that I'll talk about. But basically, the on-cue page is the master resource. So if I say something that's contradictory to the on-cue page, which I will obviously try to avoid, the on-cue page will be taken as correct until we decide otherwise, and then I'll change it. I should also say that I do expect everybody to read the syllabus very carefully, because the syllabus has tons of details about all kinds of different things that are going to be happening, especially with the details about online delivery. So please read through the syllabus carefully. So I will talk about grading a little bit. So grading has four components. There's quizzes, there's assignments, there's a project, and there's a final exam. So quizzes are worth 30, assignments are worth very little, 5, project is worth 10, and exam is worth the rest. So quizzes I'll spend some time talking about. But as I say, you should read what's written about quizzes on the on-cue page. But just so I can say the important things out loud. Quizzes will be run in the tutorials on alternating weeks. So that means even numbered weeks, there will be a quiz. It will be in the tutorial. It will run in 30 minutes will be the entire duration. In other words, from the time the quiz is made available to the time you have to submit it is 30 minutes. The questions will be designed to be significantly shorter than 30 minutes. So to give you time to download. You shouldn't have to print the quiz. The quiz questions will be simple enough that you can quickly jot them down. So if you don't have a printer, that will be fine. And then there's rules about uploading, and about how I've set the formatting for uploading. So you should take a look at that. So quizzes during the first 6 weeks during the online portion are going to be Zoom proctored, which I understand has all kinds of things that we hate about it, but I kind of have no choice. Quizzes have to be worth something. They're worth 30%, and they're worth nothing if there's no form of proctoring whatsoever. So they will be Zoom proctored. The quizzes will be administered by the TA, Henry Kavle, who's info is on the webpage. But basically the on-cue page contains all the information you need to know about how quizzes are going to be handled. One other thing I'll say about quizzes is that there's 6 of them, one every other week. The top 4 are used to calculate your 30% quiz score. And I'm expecting that you don't just sort of use the 2 freebie quizzes you have to sleep or to recover from a hangover. They're intended to be there for serious issues, especially given the climate that we're in right now. So you have only 2 allowed missed quizzes, and if you need to miss more than 2 for some reason, then that means that you're having some kind of a long-term accommodation issue, and that'll have to be dealt with separately. Okay, so make sure when you miss a quiz that it's really one you want to miss. Okay, so assignments are worth very little. As I said, they're essentially there for practice purposes. And the way the assignments are going to work is they will be due, you hand them in, and the TA is going to grade one of the questions on each of the 4 assignments that are due. And you won't know which one beforehand. There's a project. The project's due on the last day of class. The information about it is on the on-cue page. It won't necessarily make sense to you right now, so you won't be able to start it this afternoon, but you should be able to start it reasonably soon. And it's meant to be extremely simple, just sort of a little exercise in bringing together all the things that we do in the course. And the final exam, well, if we're in person in April, and who knows whether that'll be the case or not, then things will go like normal. And if we're not in person in April, then we're all going to be scrambling, and I'll be telling you how the final exam is going to work when we get to that. Okay. So that's all I can think of. There's like I said, there's more to say, but it's all on the on-cue page, so please take a look at that. Okay. All right, so any questions about course logistics? Okay, I'll assume we're good. So maybe the best thing to do is raise your hand or put something in the chat box. Then that's probably the best way to signal my intention that you have a question. Okay, so the course. Sorry. There, okay. So this is a course in sort of mathematical modeling of mechanical systems. And so what we're going to do in the course is we're going to talk about how physical notions that we're all familiar with get translated into a language of a particular kind of mathematics, namely the mathematics of differential geometry. And so what we're going to be talking about for the majority of the course is a subject which is known as geometric mechanics. So it's using differential geometry to model mechanical systems. And essentially the course is going to proceed in sort of fits and starts. We sort of talk about a physical concept, and we talk about the mathematics behind that physical concept, and then we go back to another physical concept and talk about the mathematics for that. And so the topics can kind of be arrayed like this. So we'll talk about configuration. In configuration, you can kind of think of as position. So, if you take a snapshot of your mechanical system, and mechanical systems, as we will see, are rigid bodies and particles. You take a snapshot of your system at a certain time. All the objects that comprise your system are in some formation or other. That's the configuration. And in mathematics, the set of configurations is represented by a differentiable manifold. So that's the first kind of equivalence we'll be talking about. Okay, and then there's velocity. And velocity is represented in differential geometric language by a tangent vector. And a tangent vector is probably an idea that you have maybe in your head already, and it may even correspond to velocity, but we'll see how to do that in a mathematically precise way. So we're going to talk about kinetic energy is another important physical concept. And the differential geometric object corresponding to kinetic energy is what's going to be called a Riemannian metric. And another physical concept we'll talk about is force. And force, as we'll see, is represented by a cotangent vector, which is, along with Riemannian metric, probably a new idea for you. And so the course is going to, proceed by, sort of starting here and then talking about this thing, and then starting here and then talking about this thing, and so on. And, as we sort of go along, there'll be other sort of concepts that we introduce to sort of backstop some of these things that we need to talk about. So there'll be other topics in here that are going to necessarily come up along the way, but these are sort of the sort of organizing points of how we talk about these things. Okay. Okay. So maybe we can even kind of get started a little bit today by talking about configuration. And so I'm actually going to be asking questions, and it would be super duper helpful if you were to answer the questions that I ask, or at least try to, because that just makes it more fun for everybody, or at least for me. Okay, so configuration. So as I say, configuration is kind of the set of positions of your system in some sense. And so what we'll start out with is we'll talk about some examples, just to get the juices flowing on the kinds of things we're going to talk about. Okay. So the first example will be a very simple thing, and it's just going to be a particle. Okay, so it's a particle moving in space. So space is the usual three-dimensional space with which we are all familiar. If you wanted to mathematically represent the position of a particle, what would be the mathematical object that you would kind of establish as being in correspondence with the positions of a particle? Anybody?
All three tuples of real numbers?
Exactly. So R3, right? That's not meant to be hard. And if you wanted to do that in a precise way, the way you would do it is you would choose some sort of a frame by which you measure the positions of your particle. So, and if you were to choose a different frame, you would get different positions of your particle, and so you would end up with kind of two equivalent representations of the same system. And while we're thinking about this here, the natural way to parameterize this set of configurations of this particle is to, as Christian, I think, said, is to use just the coordinate functions, the sort of x, y, z, or x1, x2, x3. But you could think about doing that in other ways as well. So, for example, if you were, and oh, there it is. My feed jammed up for a second. Okay, so, okay. Sorry about that. I think you missed some of what I was saying probably. So if we want to talk about a planar system, so just a system moving in the plane, so we just have the two coordinate axes. So you can measure the location of a particle in the plane by x and y, but you may also want to do that in a different way. You may also want to measure maybe that distance and that angle. Okay, so the system would be the same, but two different ways of kind of enumerating what the position actually is. Okay. All right. So another example. Again, not meant to be complicated, but maybe it'll help us think about some things a little more carefully, and that is just a pendulum. Okay, so it's just fixed to the ground at this point here. And it sort of just swings around, just a normal, simple pendulum, okay? Now, if you wanted to, again, just like in the first example, take a set whose points, so a mathematical object, a set, whose points are in correspondence with the positions, the configurations of that pendulum, what set would you want to choose? Anybody?
Polar
Sorry, yes?
polar coordinates.
Yeah, well, that's certainly the right idea. Polar coordinates are what? Polar coordinates, well, polar coordinates are a little bit more like what I did up here, right? So I had an R that I was kind of talking about here and a theta. Do you need an R to talk about the position of the pendulum?
Oh, right. You're
Yeah,
right.
so
So
it's
it's
really
R.
just theta, right?
Yeah.
Yeah, so it's really, so kind of where you land is an angle variable, right? That's really how you're going to parameterize the position of the pendulum, is with an angle variable. That's the natural choice. What kind of a mathematical set, if you were to say the set of angles, what's the set of angles? What is that mathematically?
Rotation.
Yeah, but I want it mathematically. You have to give me a set. So up here, we decided it was going to be R3. Okay, so I want, a real concrete
A
mathematical.
circle?
Say again?
A
I think
circle.
yeah, circle,
Yeah.
exactly. Okay, and so we're a circle is something we're going to see a lot in this course, and the circle has a name. It's called S1. S is for sphere, because we're going to talk. So a circle is like a one-dimensional sphere, and then the normal sphere of your sort of normal English language sphere is S2. But there's other kinds of spheres that you can talk about. And so S1 for us is simply going to be, it's a circle, and it doesn't matter really the radius of the circle. There is a physical radius attached to this system, let's call that R, but the angle itself doesn't really care about R, so you may as well just use the unit circle. Okay. All right, so there's a pendulum. Now let me make it a lot more complicated. A double pendulum. Okay, so it has two. This one's attached to ground, and then this one, the two links of the pendulum are fixed at that point here. Okay, so what, again, mathematical object do you think you're going to use to describe the configurations of this double pendulum?
A circle across another circle.
Exactly. Okay, so it's going to be S1 cross S1. Okay, and so we normally write the configuration space of a system as Q. Okay, so here we decided that Q was S1. Here we decided that Q was R3. And here we decided that Q is S1 cross S1. Okay, so good. So these are simple examples, and these you can more or less eyeball these and quickly get to kind of the right answer. All right. So let's talk about something that's a little less easy to see immediately. Okay, so I have this fixed point here, and then what I'm going to do is I'm going to attach to this fixed point, I'm going to attach a rigid body, okay? All right, so it's a rigid body, and this is a three-dimensional rigid body. If it was just constrained to move in the plane, then this would just be a pendulum, right? Just a pendulum that looks weird. But it's not constrained to move in the plane. It moves in three-dimensional space, and this body is the only constraint is that this point here is fixed to a point in the body. But other than that, the body can rotate freely about that point. Okay. Now, what do we think about this, again, a mathematical thing that we could use to represent the configurations of a body rotating in three dimensions?
Is that S2?
Oh, sorry, I apologize. Right. So, okay, that's a good question. Thank you for the question. The question is for the pendulum. Could you also, are there different representations? Basically, the question is, are there other sets that you could use? Okay, so it's a good question. So there's another obvious choice here, and that is you could use 0 to pi. Right, the set of angles certainly lives in the interval 0 to 2 pi, right? And you need to, at the end point, you need to either choose 0 or 2 pi. Okay, and that's absolutely correct in the sense that every position of the body is in unique correspondence with exactly one point here, but it's also in unique correspondence with exactly one point here. And so in that way of thinking about things, either of these is a perfectly valid representation for the configuration here of just a single pendulum, okay? But we prefer this one. Okay, and why do we prefer that one? Well, we kind of prefer that one because it seems to naturally have a lot more to do with the rotations of a pendulum than this one does. So, when you work with this, you kind of, you start at, let's say, an angle of 0. Okay, and then you rotate, pi over 2 pi, and you go around and you end up at 2 pi. But then, this point at 2 pi is the same as 0, but that's not really so identifiable when you when you just represent things using the interval 0 to 2 pi, whereas it is representable in the circle. And there's a real mathematical way of understanding that, and that's actually one of the homework problems. Okay. So these choices of Q are not necessarily unique, okay? But what we'll see is that there's sort of a natural way of modeling these systems, and so they may not be unique, but once you make certain choices, there's things that pop out in a fairly natural way. Okay. Okay, so sorry, thank you for the question. That's good. Sorry, now let's go back to this rigid body rotating in 3 dimensions, fixed at a point. So I think somebody was about to volunteer an answer when I cut them off by answering the question.
Is it S2?
Right. Okay. So that's a good guess. Okay. So let's maybe think about. Let me see if I can sort of dig into whoever's mind answered that question, and sort of see if I can see why S2 maybe is what they came up with. So the idea is that let's maybe take a little stick. Right, and this thing is sort of attached to the body. Okay, so as your body moves around, the little stick moves around, and the idea is that, but you keep track of so here's fixed at this point. Here's my little stick, and as the body moves around, the stick moves around too. But why doesn't that work? Can anybody think about what the problem is with that characterization? What's missing in terms of the motion of the body when you try to just use this little stick to find the configuration of the body?
Is it that the rotation about the stick itself?
Yeah, that's right. So you're missing this, right? Right. And so there's a rotation there. And so you think, okay, I got it now. It's S2 cross S1, but it's not. Okay. But that's a very good guess. And basically, you know, the rationale for that guess is kind of exactly what I just said. You know, you seem to get some of it by doing this, you know, sort of stick that's attached to the body, and then the other. But the problem that happens is when the rotations become large. So this works kind of, you know, if you're going to sort of take the reference rotation and only move a little bit around. But if you're going to take large rotations, then this becomes problematic. And what you see, if you think about that for a second, is that you end up with non-unique representations in here of the same position of the body. Okay, so and you need for this, whatever this mathematical object is, you need for it to be in one-to-one correspondence with the positions of the body. Okay, and this fails to do that, it turns out. Okay, but that's a very good guess. Other guesses? Well, you know, what dimension should this thing have, do you think? Well, you know, we kind of think that S2 is two-dimensional, right? And S1 is one-dimensional. So, you know, one of the nice things about this guess was that it's three-dimensional, and, you know, it makes sense. There's kind of three ways that a body in 3 dimensions can rotate. Okay, so we need something that's three-dimensional, whatever it is. Any other three-dimensional things you can think of that might be natural candidates? Well, just based on things we've talked about so far. Here's something that's three-dimensional. What do you think? Could you make that work? And so the idea is, you know, you're going to kind of maybe measure the rotations about the x-axis and the y-axis and the z-axis is kind of the idea there. Okay. And that is going to run into the same kinds of problems as this one did. For large rotations, there's really no such thing as, you know, decomposing a rotation into a rotation about each of the 3 coordinate axes. That doesn't work. Okay, so so this one's not right. This one's not right. The only other, based on what we've done so far, which is very little, the only other three-dimensional thing that we've talked about is S3. Okay, so this is just the three-dimensional sphere in 4 dimensions. So it's just the set points in R4 of unit length. Okay, of those 3 guesses that I've shown you so far, S3 is the closest, but it's still not right. Okay, and the fact of the matter is, you need to not guess. You need to come up with a systematic way of putting this together. So let me sort of illustrate to you how you do that. Okay, and I'm going to do that with my hand. Okay, so don't look at this, the shared screen, look at my hand. And so the idea is you do rather like we did up here with R3, and that is you choose a coordinate frame and you fix that coordinate frame. And obviously you're going to fix that coordinate frame so that its origin is at this fixed point here. Okay, and let me call the axes of this frame, let me call those S1, S2, and S3. Okay, and S, as we'll see, stands for spatial. All right, so I fixed that coordinate frame. Okay, now I'm going to take another coordinate frame. Its origin is going to be at the same point, but this coordinate frame is not fixed in space. This coordinate frame moves when I move the body. Okay, so it's fixed to the body. Okay, and as the body rotates, this frame rotates too. It's attached to the body. Okay. And so we can maybe kind of draw that thing on this picture, like so. So maybe like this. So B1, B2, B3. Okay, and there's now issues of orientation come in, right? And I've used my right hand here, so so we fixed a right-handed orientation of this frame. Okay, so it's 1, 2, 3. Okay. So can everybody kind of see me when I do this on my little thumbnail there? Okay. There's a few times in the course where it's going to be helpful to do stuff like that. Okay, now, so that's what I've done. I've taken two orthonormal frames, okay, and they're fixed relative to each other. One's fixed relative to space, and then the other one moves around with the body. Okay, now how can I use that data to generate configurations? Well, if you think about it, now the body is obviously uniquely determined by the position of this frame that's fixed with the body and moves with the body. Okay, so if you wanted to assign a unique configuration of the body, what you need to do is you need to tell me what those vectors are, B1, B2, and B3, in a certain position. And the natural way to do that is to take the components of B1, B2, and B3 relative to S1, S2, and S3. Okay, and so what I do is I represent those in a matrix. Okay, and so I do this. I have B1, 1. I'll write it like that, and I'll tell you what that is. B1, 2, 2, and B1, 3. Okay, and so these are I'll write it down what they are in a second. But here I'm going to have B2, 1, B2, 2, B2, 3, and B3, 1, B3, 2, B3, 3. Okay, and B, J, K is the kth component of the vector Bj in the basis S1, S2, S3. Okay, so I build this matrix. Okay, now finding those components is actually fairly easy. Okay, and it's fairly easy because this basis, I'm gonna declare that this basis is an orthonormal basis. Okay, so each of the vectors has unit length with respect. So I'm in R3 now, right? My physical system is in R3, so I have an inner product, the normal R3 inner product. Okay. Which has physical meaning, okay? And this basis S1, S2, S3 is orthonormal with respect to that Euclidean inner product, which when you were a small child, you called the dot product, okay? But we call it the Euclidean inner product, right? So, so with respect to the Euclidean inner product, S1, S2, and S3, and also B1, B2, and B3, all those vectors have unit length, and they're orthogonal to one another. That's what it means to be orthonormal, okay? So if you want to find the components of a vector V, an arbitrary vector V in R3 relative to an orthonormal basis, let's say S1, S2, S3, that's very easy. Do you remember how to do that? How do you find the components of a vector in an orthonormal basis?
Projection is in the products.
Yeah, just take inner product, exactly, okay? The components are simply the inner product of V with S1, V with S2, and V with S3. Okay, so what this means, therefore, is that BJK is simply the inner product of BJ with SK. All right, so this is a thing you can calculate relatively easily. Okay, all right, so we have this matrix, and this matrix, just by the way we've constructed it, every such matrix that looks like this, okay, is in one-to-one correspondence with the configurations of this rigid body. Okay, and so the set of all matrices that look like this, and what does look like this mean? Look like this means that they are the components with respect to S1, S2, and S3 of some other orthonormal basis, B1, B2, and B3. Okay, so the set of all such matrices is necessarily exactly the configuration space of this rigid body that's rotating about a fixed point. Okay, but what is the set of all matrices like that? Okay, if you take what I've done here, two orthonormal bases, and you take the components of one orthonormal basis, say B1, B2, and B3, with respect to the other orthonormal basis, S1, S2, and S3, and you do like I've done here, and you assemble them in the columns of a matrix. So first column, second column, third column, okay? What property does that matrix have? It's not just an arbitrary matrix. You can't find any three by three matrix in that way. A matrix which is built in this way has very special properties. So for instance, let me try to coerce an answer out of you. So for example, you know that each column of this matrix, okay, has unit length, right? Because it's the components of a unit vector in an orthonormal basis, okay? So the sum of the squares of the components of the columns of the matrix add up to 1. And we also know that each of the columns of this matrix is orthogonal to all the other ones. Do you remember what such a matrix is called?
Is that the orthogonal matrix? Something
That's
like
right.
this?
It's what you called in 212, I would imagine, an orthogonal matrix. Okay, so the matrix. So let me call this matrix here. Let's call it R. Okay, so big R for rotation. Okay, so the matrix R is an orthogonal matrix. Okay, so I've just given you one characterization of orthogonal matrices, namely that their columns and also their rows are unit vectors that are all orthogonal to each other. So that's one way of characterizing an orthogonal matrix. Can you think of, do you remember another way of characterizing an orthogonal matrix? There's a simpler way. Just a simple formula, R involving R, that characterizes what it means to be orthogonal.
R times R transpose is the identity.
Thank you. And it's equivalent to saying this. Okay. And so generally then, we have this set O, let's call it ON. And so ON is going to be, so these are 3 by 3 orthogonal matrices. So we have ON, which is going to be N by N orthogonal matrices. So these are the R's in the set of N by N orthogonal matrices. Sorry, the set of N by N matrices. Okay, so I'll denote the set of N by N matrices by R to the N times N. Okay, that satisfy this this relationship. Okay, so that's what we call This is called the ON. O obviously stands for orthogonal. And this is called the orthogonal group. Okay, and it's a group because when you take two orthogonal matrices and you'll multiply them together, you get another orthogonal matrix. Okay, that's probably a homework problem or maybe an exam problem or something that you've had in the past. Okay, now the orthogonal matrix that you get in this case, this one here, it's not. It has an additional attribute. Okay, now what do we know about this relationship? What does this relationship tell you about the determinant of an orthogonal matrix? If you take determinants of this formula, well, the determinant of a product is the product of the determinants, and the determinant of a transpose is the same as the determinant. And so this tells you that the determinant of R squared is equal to the determinant of the identity matrix, which is 1. And so you know that the determinant of an orthogonal matrix is either +1 or -1. Okay. What do you think this orthogonal matrix determinant will be? Will it be +1 or -1?
Plus,
Yes, it's plus. Can you think of a reason why that might be?
because it's like respecting the orientation of the rigid body.
Exactly. And so that's exactly the right answer. And so one way to think about that, kind of in a geometric way, is as follows. If you take your S1, S2, S3 frame, there's going to be a configuration of the body where B1, B2, and B3 lines up with S1, S2, S3. Okay, and the determinant of this matrix R in that case will definitely be 1 because R will be the identity matrix in that configuration. Okay, now as I move things around, okay, the determinant can't suddenly change from +1 to -1. There's kind of a continuity of the determinant going on there. And so if the determinant is +1 at some configuration, it's necessarily +1 at every configuration. And so as a consequence of that, we introduce this thing which we call SON. And this is the set of orthogonal matrices with unit determinant. And this is called the special orthogonal group. Okay. And again, this is a group. So ON is a group, and SON is a subgroup of ON, because if you take two matrices with determinant 1 and you multiply them together, you still get a matrix with determinant 1. So SON is a subgroup. Okay. And so the big sort of punchline of the lecture today then, at least of this last example, is that the configurations of a rigid body fixed at a point are represented by SO3. Okay. So that's, sorry, I apologize. There's a chat question here. Well, so what makes the determinant function continuous is the question. Well, if you think about the determinant is just a polynomial function of the entries of the matrix, right? So, just think about how you calculate the determinant. And polynomial functions are continuous, so the determinant is a continuous function. Okay. All right. Okay, so that's all I'll say for today. And so next time we're going to pick up, and we're kind of, going to begin the first step of this process that I described at the beginning of the lecture. That's going to slowly scroll through here. And we're going to talk. So today we've talked about configuration. We're going to have more to say about configuration later. But in order to say more about configuration, we need to talk about differentiable manifolds. So that's what we're going to do next class. Okay, so that's the end of the lecture, and I will therefore stop the recording here. But if anybody wants to ask questions, they can. But I'll stop the recording now.